Hello everyone, welcome to the 8th week of discussion session of the course Strength of Materials course offered by NPTEL. Course instructor of this course is Professor Siman Kumar Bhattacharya, is a professor from IIT Kharagpur. Myself, Asif Raza, I am a teaching assistant. I am a PhD scholar from Department of Civil Engineering, IC Bangalore. So this session would include the discussion of questions relevant to assignment number 8 because the due date for the assignment 8 is still not over, so we'll be discussing questions relevant to assignment number 8. So uh, let's start. So for this session we need one basic formula to remember, that's the Flexrel formula, and that is like M by I F or what is that, sigma 1. So this is the formula, and here the bending moment. Normally the units would be in kilonewton meter or something like that. Then is second one. It's only millimeter to the power 4. Then sigma is the bending stress. That is Newton per millimeter square. Then megapascal, something like that. Then y is the distance from the neutral axis where this trace is compared to. That's a length unit, so let us keep it in millimeter. Then A is Young's modulus, or modulus of elasticity. The unit is in megapascal or Newton per millimeter square. Is the radius of curvature of the curve. Okay, so for this session, it's best to remember this formula because it will be widely used. Okay, So let us keep this in mind and let's start. So the first question for today's session is this. Question is, a cantilever beam of rectangular cross section is 1 meter deep and 0.6 meter wide. If the beam were to be 0.4 meter deep and 1 meter wide, then the flexural capacity of the beam would be weakened by 0.6 times. Flexural capacity of the beam would be weakened by 0.27 times, or the flexural capacity of the beam would be strengthened by 0.6 times, or the strength of both the beams would be the same. So in this question, we are given with a cantilever beam of rectangular cross section. Earlier, its depth is 1 meter and breadth is 0.6 meter. Then in the the second case, beam depth is 0.4 meter and 1 meter breadth. We need to find the flexural capacity and compare them. So flexural capacity would imply the moment carrying capacity of the section, that is. So let us write that formula again first, that is M by I sigma by Y E by R. Okay. So for this we'll use this first two formula, and this would give me I by Y. Okay, and if you go through the literature, you'll come across that I by Y is called as sectional modulus. Okay, modulus, and for this case, mm, so if you see this formula, if everything is kept same except the the geometry, so kind of our moment carrying capacity is directly proportional to Z. Okay, so uh, uh, and what is Z? Z is I by Y, and I is BD cube by 12, and Y would be kind of if we are finding the moment carrying capacity of the section, so Y should be max, so it would be D by 2. Thus our sectional modulus for rectangular section would come out to be BD square by 6. Now to find the relation, so M1 by M1 upon M2, or M2 upon M1 would be equal to what? B2 upon B2 by D2 square upon B1 by D1 square. Okay, thus M2 by M1 would be equal to what? M2 is 0.4. I'll just write it here. So B1 is equal to 1 meter, D1 is equal to 0.6 meter. Oh, sorry, this is 0.6 meter, D1 is 1 meter, B2 is 1 meter, and D2 is 0.4 meter. Right, yeah. Now let us write them. So B2 is 1, D2 is 0.4 square upon B2, B1 is 0.6 into D1 square. This is equal to 0.16 upon 0.6, and this comes out to be nearly 0.27. So F2 is equal to 0.27 M1. The kind of M2 reduces by 0.27 times of M1. Thus, uh, uh, correct answer would be option B. The flexural capacity of the beam would be weakened by 0.27 times. Okay, I hope it's clear now. Moving on to the next question. Cantilever beam of length 2 meter has cross section of 10 mm by 10 mm. It carries a transverse load of 10 Newton at a distance of 1.5 meter from the fixed end. The maximum bending stress in the beam is. So first thing first, we should write what all things are provided. So we are given with the question is a cantilever beam with the length of 2 meter and has a cross section of 10, or I'll just write it here. B is 10 mm and D also 10 mm. It carries a transverse load of 10 Newton at a distance of 1.5 meter from the free end, from the fixed end. So we need to calculate the maximum bending stress for this case. Okay. So now let us write what is the flexural formula, which I told you at the starting of this session. That is M by I sigma by Y E by R. We need to calculate the maximum bending stress. For this, we'll use the first two relation, and that will give me sigma is equal to M by I times Y. We just need to use this. Okay, so to calculate sigma maximum bending stress, we need to know what will be my bending moment. That would be max I, and this would be Y max. Okay, now for this section, for this structure, what would be my bending moment diagram? It would be uh, so 1.5 and 2.5. Okay, so 10 into 0.5, kind of it will be 15 Newton meter here. 15 Newton meter. Yeah. So this my moment maximum bending moment come out to be 15 Newton meter, and I is what, BD cube by 12. Okay. So Mm, okay. So what we'll do is we'll keep this in Newton mm. We'll convert this into Newton mm. So that will be kind of 1.5 into 10 to the power 4 Newton mm. I would be BD cube by 12. I'll just substitute it in the formula, and Y max would be D by 2. Okay, let's substitute this. So 1.5 into 10 to the power 4 D by 2 is 10 by 2. This would be 10 cube by 12. So correcting it, we'll get what? 1.5 12 5. This would be equal to what? 12 into 5 60, 90 megapascal. But check the calculation. So with my calculation, it comes out to be 90 megapascal, and thus we can say the correct answer would be option B, 90 megapascal. So for the question, a cantilever beam of length 2 meter with a square cross section of 10 by 10 mm, it carries a transverse load of 10 Newton at a distance of 1.5 meter from the fixed end. The maximum bending stress in the beam comes out to be 90 megapascal. Okay. Now moving on to the next question. So question number 3 for today's session is question is determine the maximum tensile stress due to pure bending by positive bending moments M for a simply supported beam having a cross section of diameter D, circular cross section of diameter B. Okay. So for this, so question is we are given with a simply supported beam. And there's a pure bending by positive bending moment M. If I keep this as L, this should be like this. So yeah. So for this, what should be my bending moment diagram? So for this to calculate, we need to know what would be no. Okay. Question is like this. So it's subjected by positive bending moments. So if the question is like this, okay. Now we need to know what would be the reactions. R A B. So if I say this is R A R B. The moment about B equal to 0 would imply RA times L plus M minus M equal to 0. This would give me R equal to 0 and sigma Fy equal to 0 would give me RA plus RB. 0 implies RB equal to 0. Okay. The bending moment diagram would be throughout this section there would be a positive bending moment diagram. Yeah. Yes. So that's why it's a pure bending case. Now from A to B. Now coming into the question, we need to find the maximum tensile stress. Maximum tensile stress. Okay. So let us write the flexural formula again. Flexural formula again, and that is M by I sigma by Y E by R. Using the first two relation, M by I equal to sigma by Y, and this will give me sigma is equal to M by I times Y. Now to get the maximum tensile stress, we need to just substitute the relevant details, and that would be M. We do, that maximum bending moment comes out to be for this case is M. I is BD cubed by 12, and Y would be D by 2. And just calculate the relevant stuff. And okay, sorry. The question is having a circular section, so I is actually 5d4 by 30, 5d4 by 64, and so for circular cross section maximum would be d by 2. So y would be d by 2 again, and sigma will come out to be 32 m by pi d cube. 32 m by pi d. That is option A. So you can see for the case of pure bending, stress, maximum tensile stress would come out to be 32 m by pi d cube. And that is my option A. Moving on to the next question. Question is, determine the maximum normal strain produced in a steel wire of diameter 2 mm when it is bent around a cylindrical drum of radius 1 meter. We can see it in the figure. So here we need to find the maximum normal strain produced in a steel wire of diameter 2 mm when it is bent around a cylindrical drum of radius 1 meter. So if you see, this wire is bent around this cylindrical drum. So R is equal to 1 meter and D is 2 mm. Okay, this is what is given. Now better say it properly. This is quite a good question. We need to calculate the strain, normal strain, maximum normal strain, right? Let us write the flexible formula first. M by I sigma by Y E by R. Now, if you want to calculate strain, uh, that would be computed using the class 2 relation, and let us write that sigma Y E by R. Okay, so this R and this R is different one. Okay, so kind of sigma by E would be Y by R. Okay. Now sigma by E is what we need to compute, that is the strain we are talking about, and Y. Okay, so we are computing the strain produced in the steel wire. Now if we see, let me draw this section, and we have the wire above it, right? I'll just try to exaggerate a bit so that you guys can see it properly. This is the mid section. Now we want to compute the strain produced in this still wire, right? So maximum strain or stress would be occurring at this endpoints here and here, and that would be around like d by 2, d by 2. Okay, so the y would be equal to d by 2, and r, this r, like so r would be, we need to consider this mid section of the uh, wire. So we have to write the curvature of this mid section, and rather I should write it this r as like this, a bit cursive one. Thus r is equal to r plus d by 2. Okay, better see it properly. This strain would be under sigma by E, and this would be equal to pi by R, and that is equal to d by 2 upon R plus d by 2. And that is equal to d is 2 mm, so 2 by 2, R is 1 meter, so we'll write it as 1000 mm plus 2 by 2, it is 1 upon 1000 plus 1. So kind of so then outcome ought to be 10 to the power 3. Let's see the formula. So this would come nearly 10 into 10 to the minus 4 strain. Okay, because if I write it as 1 upon 1000, so that would be around 10 to the power minus 3, and if I write 10 into 10 to the power minus 4. Yeah, so with that, the correct option would come out to be option C, 10 into 10 to the power minus 4. Okay, this is this is a good question. So don't directly substitute the value given, like most of the people do wrong here. They would substitute the value of r is equal to 1 meter directly. uh, for the given case, it comes out to be, it will come out to be the same, like 10 into 10 minus 4, but there could be, like, if the d of the depth or the diameter of this tape would have been a comparable one, then you guys might come into trouble. Okay, so yeah, better check that properly. Moving on to the next question. Question number 5 for today's session is: the width of the strongest beam of a rectangular cross section that can be cut out of a cylindrical log of wood whose diameter is 400 mm would be. Okay, question is, we need to uh, find the width of the strongest beam of a rectangular cross section that can be cut out of a cylindrical log of wood whose diameter is 400 mm. Let me try to explain this by drawing the figure. A cylindrical log of wood, we are provided with a cylindrical log of wood. That would imply there is a circular cross section with a diameter of 400 mm. Now we need to cut out a rectangular cross section uh, from this log of wood. Okay, so what I will write is, I'll write the diameter of the log as capital D. Okay, so we want to cut out this rectangular log such that it is the strongest cut out from this. Okay, let me write this is my D. Okay, yeah, so we need to find what would be my big. Yeah, let's do this. So from the figure itself you can like guess that one of the relation will be b square plus d square is equal to d square, right, from Pythagoras theorem. Okay, now for the strongest beam, as we uh, uh, went through the first question, the strongest beam would be decided by the one which is having the maximum sectional modulus. Okay, and maximum sectional modulus is computed by I by y, that is equal to bd cube by 12 upon d by 2, and that is bd square by 6. So for the rectangular section, uh, uh, so this must be maximum. Okay, so we want this to be as much as possible, as big as possible. uh, okay, now z can be written now as b d square minus b square, so everything would be in terms of uh, b only. Okay, and b d is, I'll just substitute it, 400 square minus b square, so that will clear that there is one unknown here. Okay, now for z to be maximum, we can take this dz by db equal to 0. Okay, uh, so let us compute it. Rather, we can just write this b by 6 400 square minus b square equal to 0, and this would be uh, 1 by 6 400 square minus b square, then plus b by 6 minus 2b equal to 0. 6 going this way, then 400 square minus b square minus 2b square equal to 0. This would imply 3b square is equal to 400 square. B would be equal to 400 by root 3. And okay, will be equal to 400 root 3 mm, and this would be equal to this would be equal to 230.94 mm. Yeah, so for that my correct answer would be option D, 230.9 mm. Okay. I hope nobody will face any issues with this. It is quite a easy question. First, we just need to apply that trick to find the maximum sectional modulus. Like, to have a strongest beam, we need to have the maximum sectional modulus, and for the sectional modulus to be maximum, we just need to take the derivative of sectional modulus with respect to the width of that beam to get the and equate it to 0 to get the exact value of b. See here. Okay, now moving on to the next question. So in a next question is, in a simply supported beam of triangular cross section with depth h, the maximum shear stress occurs at a distance of, and options are h by 4 from the bottom of beam, h by 3 from the top of the beam, h by 6 from the neutral axis, and h by 5 from the top of the beam. Uh, so given question is it's a simply supported beam with a triangular cross section. Okay, with the depth h. Okay, so where the maximum shear stress would occur. So for this, we know that uh, um, that the neutral axis is located at h by 3 from the bottom. from the bottom of beam, right? So if this is my neutral axis, this would be kind of h by 3. Okay. Now the maximum shear stress occurs at h by 2 from the bottom of beam okay, at the bottom of the beam or the top of the beam, so it would be kind of h by 2 from the top or bottom. So with that, like, we can eliminate A, B and D options. So consequently it should be C, but let us confirm it. So the exact distance, so the maximum shear uh, stress occurs at a distance of h by 2 minus h by 3, that would be equal to h by 6 from the bottom of the beam. Oh, sorry, not from the, but from the neutral axis. Okay, what I'm trying to say is, this is suppose A, where my maximum so this is kind of h by 2, so this is h by 6, the neutral axis. This correct answer would be option C. So in a simply supported beam of triangular cross section with depth h, the maximum shear stress occurs at a distance of h by 6 from the neutral axis. This is quite a straightforward question. So now let us move on to the next question. Question number 7. At a section of a beam, shear force is F with zero bending moment. The cross section is square with side A. Point A lies on neutral axis. Point B is midway between neutral axis and the top edge. If tau and tau B denote the shear stresses at points A and B, then the value of tau and tau B, tau A upon tau B is, and the value options are 0, 3 by 4, 4 by 3, and option D is none of the above. So the question is given about a square cross section, right, with A as the side length. Now a neutral axis would be midway, right, A by 2. The points are A lies on the neutral axis and B lies on the midway of the neutral axis and the top edge. So this would be kind of A by 4. A by 4. Yeah. Okay. We are given with the shear force as B. Okay. Yeah. So for this, we need to know is shear stress at any cross section is given by the relation tau is equal to VQ upon IB, where V is the shear force acting, Q is area times Y bar, and I is the moment of inertia of the section, and B is the width of the section considered at where we are trying to compute the shear stress. Okay. So for the A, or uh, so V is equal to F. Okay. Uh, I is equal to B d cube by 12. Now tau A would be equal to what? F. Q is um, B d uh, and um, area of the top section, uh, B times, okay, why am I writing this way? Let B by dq by 12, so this would be kind of A4 by 12, right? Now B t by 2 and A bar would be T d by 4. Okay, and this would be dq by 12 and B. So since everything is A, B is equal to A and D is equal to A, this can be simplified and written as 4, 3, 3 by 2. Okay, now to compute tau B, that would be like PQ by IB, and B would be F, I would be the same, B dq by 12, and this would also be same. Q would be like area above this is and B will have T by 4, then this would be D by 8. So D by 2 minus D by 8. Let's write everything in A. So this would be kind of A5 by 12. AQ by 4. Here it will be 1 by 2 minus 1 by 8. Kind of 12 F by A square to 1 by 4. This would be 4 minus 3 by 8. this or this one would be 9 by 8 f by a square tau b. Now we can write tau a by tau b would come out to be 3 by 2 upon 9 by 8. So this would be kind of 3 by 4, that is 4 by 3. Yeah, thus our correct answer would be option C, 4 by 3. Hope this is okay. So this is a complex question. In this question, a safe force with zero bending moment is provided. The cross section is square with side A. Point A lies on the neutral axis, while point B lies in the midway between the neutral axis and the top edge. We need to calculate tau A and tau B and take the ratio of it. So to calculate shear stress at any cross section, the formula is VQ upon IB, where V is the shear force, where the given question is F. I is the moment of inertia, that is BDQ by 12, and that would again simplify to A to the power 4 by 12. And then Q is A times Y bar, where A is the area above the section where we are trying to compute the shear stress. So to compute shear stress at A, that is half of the beam, so it would be B into D by 2, and the centroid of this considered section would be D by 4 from the neutral axis. Now just similarly, we will compute for shear stress at B, and for this area considered would be B times D by 4, and the centroid of this considered section would be D by 2 minus D by 8. Now, like completely changing everything, like B equal to D equal to A, will get the required relation as 9 by 8 f by a square, and taking the ratio of tau A by tau B would be comes out to be 4 by 3. Oh, yes, yeah, okay. Now moving on to the next question. A simply supported timber beam with 150 mm width and 200 mm depth carries UDL over a span of 8 meter. The permissible stresses are 30 Newton per mm square in bending and 3 Newton per mm square in shear. The maximum load which can be carried by the timber beam will be. So first thing first, we need to write all the things which are given. They are given with the depth of 150 mm, sorry, width of 150 mm, depth of 200 mm, length of the intersection is 8 meter. You can write it as 8000 mm. Now maximum permissible stress in bending is 30 Newton per mm square, and in shear it's 3 Newton per mm square. You need to calculate omega max. So for simply supported beam, where you guys still don't know about this, so write there like this. W. So bending moment diagram is this, and here it comes out to be W L square by 8. This is my bending moment diagram, and shear force diagram would come out to be WL by 2. Sorry, I made a mistake here. At the center only, okay. WL by 2. Now you can so you can see that M max is WL square by 8 and V max is WL by 2. Now let us calculate the maximum load using its cases. First case, bending 1. Case 1, bending. So to calculate stress, we just need to use this formula. Okay. So this you just need to substitute. M max is W L square by 8. I is BD cube by 12. Right, it's a rectangular cross section. Yeah. Sigma B is 30 and Y is D by 2. So W will come out to be 30 times BD square by 6, 8 by L square. Let us compute it. B is what, 150, T is 200. Yeah, 6 to 8, 1000 square feet or 8000. So this is like 30 to 150, 200 and to 8 divided by 6 divided by 1000 square. So this comes out to be 3.75 Newton per mm. Or omega would come out to be 3.75 kilonewton per meter. Okay, now let us take the case shear. For this, the formula is tau is V by I Q by B. VQ by B. So tau is maximum is WL by 2. V is sorry. So tau is given as 3 Newton. Yeah, this is 3. V is WL by 2. Q would be maximum would be in the neutral axis, so kind of B d by 2 times d by 4. This would be B d cube by 12 and B. Okay, now just simplify a bit more. This is WL, 2 to the 4 for the 16. Okay, in the numerator 2. Okay, let's write it like this. So this is BD square by 8 upon B square d cube by 12. Thus W comes out to be 3 B square d cube by 12 divided by BD square by 8 times L by 2. That is 3 BT square removed, so it would come out to be VD by 12. Down it would be BT square removed, so L by 16 left. Now again simplify 3, 4, 4, 4. This would be 4 BT by L. Thus 4 B is 150. Yeah, 150. D is 200, and this was 8000. This would come out to be 4 into 150 into 200 divided by 8000. This comes out to be 15 Newton per mm, or 15 kilonewton per meter. So if we see both, like so from bending it comes out to be 3.75, while from shear it comes out to be 15 kilonewton per meter, and out of this two, to be on the safe side, we need to take the lesser of these two, and thus our correct answer would be option A, 3.75 kilonewton per meter. So maximum safe load would be lesser of 3.75 and 15, and that is equal to 3.75 kilonewton per meter. Okay, this is also a good question. Yeah, moving on to the next question now. Yeah, so question number 9. So the given figure, all dimensions are in millimeters, shows an I section of the beam. The shear stress at point P, very close to the bottom of the flange, is 14 megapascal. The shear stress at point Q in the web, very close to the flange, is options are indeterminable due to incomplete data. B is 60 megapascal, C 70 megapascal, and option D is 14 megapascal. So if you see, the point P is where at the very close to the bottom of the flange, and Q is in the web, and but that is close to the flange itself. So like if I say we need to compute the stress at Q itself, or rather I'll write we now know the formula to compute the shear stress, and that is kind of tau is equal to VQ upon IB. Now if we see both P and Q, both will be having V, Q and I as same. What they will differ is B. So tau P by tau Q would be VQ upon VP. This is it. So tau P is already given as 14 megapascal. We need to compute tau Q, right? And VQ is the width of the web, that would be kind of 20, and BP is width of the flange, that would be 100. So tau Q will come out to be 14 into 5, that would be 70 megapascal. The answer would be option C, 70 megapascal. Yeah. I hope this is okay for you all. Moving on to the next question. Question number 10 for today's session is a 4-meter long beam of 400 depth is subjected to concentrated loads as shown in figure below. Given the allowable stress in bending is 30 Newton per meter square and W value is 160 kilonewton. The minimum width of the beam is to calculate this. Let us first write what all are given. So we are given with the length of the beam as 4 meter, that is 4000 mm. Depth of the beam as 400 mm. Sigma B is 32 Newton per mm square. W as 160 kilonewton, or 16 into 10 to the power 4 Newton. So for the given case, shear force diagram is will come out to be L by 3, L by 3, L by 3. So we are solving this question where the length of the beam is given as 4 meter with the depth as 400 mm, and it is subjected to concentrated loads as shown in the figure. There are two concentrated loads. Loads are acting at L by 3 from the ends of the simply supported beam, and allowable stress in bending is given to be 32 Newton per meter square, and the value of the concentrated load is 160 kilonewton H. We need to find the minimum width of the beam. So for that, first we need to compute what is uh, uh, bending moment diagram. So with that, we'll be able to see what would be the maximum bending moment occurring in this section, and this would be equal to W this and this. So it will come out to be W L by 3. Yeah. The maximum bending moment comes out to be W L by 3. Now we need to add the flexural formula again, and that is M by I sigma by Y E by R. For this question we need to use the first relation. Yeah. So I'll just write it. M by I sigma by Y. M is WL by 3. I is BD cube by 12. Sigma is just now write it as sigma B. Y is D by 2. Now we want to calculate B. So just keep everything this side. B would be equal to WL by 3 upon D square by 6 times sigma B. Now let us substitute the values, or okay, let me simplify it more. So this would be 2WL sigma B D square. Now let us substitute the values. B will be equal to 2. W is 160 kilonewton, so that is 116 into 10 to the power 4. L is 4000 mm. Sigma B 32, and D is 400 square. Let us compute it. So 16 into 32 gets cancelled out. So we're left with 4000 into this divided by 400 square. The answer comes out to be 250 mm. Thus answer would be option D, 250 mm. Okay, I hope this is okay. Moving on to the next question. Let me take a break. So moving on to question number 11 of today's session. The question is, the beam A has a width B and depth D by 2, while beam B has width B by 2 and depth D. If bending moments applied to both the beams are the same, the maximum bending stresses induced in cases A and B are related So first thing first, we need to write the flexural formula, that is m by I sigma by y equal to E by R. Using the first two relation, sigma comes out to be m by I y. For rectangular cross section, this can be again simplified. Mi is bd cube by 12 and y is d by 2. Thus, sigma is 6m by bd square. Okay, now coming into the question, we can write sigma a is equal to 6m, width is b and depth is d by 2, right? So this is equal to 4 times 6m by bd square. Now sigma b is 6m, width is what, b by 2 and depth is d. So this is 2 times 6m by bd square. Thus, if I compare this to sigma a is twice of sigma b. The answer would be option B. Question number 12. So a 0.2 mm thick tape goes over frictionless pulley of 25 mm diameter. If E of the material is 100 gigapascal, then the maximum stress induced in the tape is. So this question is similar to what we were finding in the normal string part. Yeah, so kind of we have a frictionless pulley over which thick tape goes. There's a mid section, and this is 0.2 mm thick, and this has a radius. Okay, complete thing has 25 mm diameter. Yeah, so you can write as D as 0.2 mm, capital D as 25 mm, and E is given out to be 100 gigapascal or 10 to the power 5 megapascal. Now writing the flexural formula, m by I sigma by y e by r. For this case we need to use the last two relation. That would give me sigma by y is equal to E by R. To calculate the maximum stress, we just need to use E by R. E is given out to be 10 to the power 5, y would be equal to t by 2 and R would be equal to d by 2 plus d by 2. this would be equal to 10 to the power 5. D by 2 comes out to be 0.1. This will come out to be 12.5 plus 0.1. That is 0.1 divided by 12.6 times this comes out to be around 793.65 megapascal. So round it, we can get 800 megapascal. Correct answer would be option D, 800 megapascal. Okay, moving on to the next question. A simply supported beam of rectangular cross section of span L carries a concentrated load W at midspan. If the width of the beam is given as B is constant and depth is varying throughout the span, then what should be its midspan depth when design stress is F? Okay, so we're given that simply supported beam with the span length as L UDL as oh, not the UDL but concentrated load W at the midspan we can draw the bending moment diagram for this case, and it will come out to be WL by 4. Okay. So now writing the flexural formula, that is M by I sigma by Y E by R is using the first two relation, then this would be sigma by Y. Let us write everything what is given. So M will be equal to WL by 4, I is BD cube by 12, sigma is equal to F, Y is D by 2. So okay, what we want to compute is depth of the beam. So WL by 4 and write F times BD square by 6. Again, D square would be WL by 4 F B 6. This is equal to 3 WL by 2 F times B. This would be equal to D square. Thus D should be equal to root of 3 WL by 2 FB. Yeah, so correct answer is option C. Hmm. This is quite easy. You just need to find the bending moment. Uh, uh, since the design stress is already given as F, we need to substitute the maximum bending moment M, and that is WL by 4, and thus the depth at that section would come out to be this. Okay, moving on to the next question. Uh, okay, question is, if a circular shaft is subjected to torque T and a bending moment M, the ratio of maximum shear stress to the maximum bending stress is, so for this, first thing first, uh, this is a circular shaft, okay, subject to torque T and bending moment M. The flexural formula is M by I sigma by Y E by R. So maximum bending stress can be written as M by I times Y using the first two relation. So for the circular section, this comes out to be M pi d4 by 64 and Y is d by 2. So sigma b is 32 m by pi d cube. Yeah, yes. Now using torsion formula, if you remember two sessions earlier, it was T by IP tau by R d theta by L, right? So by using the first two relation, tau can be computed as T by IP times R. This is equal to T. IP is polar moment of inertia, and that is pi d4 by 32. R is d by 2. So this comes out to be 16 T by pi d cube. The since comes out to be 16 T by pi d cube. We want to compute tau by sigma b, right? And that will come out to be I'll just take the numerator now, 16t upon 32m, and this is equal to tau by sigma b is t upon 2m. So this is 8. Correct answer would be option B, t upon 2m. So for this you just need to remember these two formulas. One is flexural formula, other is torsion formula. In the flexural formula we use the second moment of area or the moment of inertia, while in the torsion formula we use the polar moment of inertia. Now moving on to the next question. A rectangular beam of 10 cm width is subjected to a maximum shear force of 50 kN and the corresponding maximum shear stress is 3 MPa. The depth of beam is, this is a rectangular beam with width as 10 centimeter, that is equal to 100 mm. Now maximum shear force V is 50 kilonewton or 50 into 10 power 3 Newton. Then tau is given out to be 3 megapascal. Depth of beam is what? So we can pursue this like computing directly or using shortcuts. So as earlier I have been following like conventionally, this time I will try to use directly. So for rectangular section we know that tau max is equal to 3 by 2 times tau average, and to compute tau average or average shear stress, that would be equal to V by Vd. Okay, so let us substitute everything now. 3 by 2, V is 50 into 10 power 3, V is 100, and we want to compute T. Okay, this 3 cancel out, 200, 50, so 4D is equal to 10 power 3, thus D is 1000 by 4, 250 mm, okay, or 25 centimeter. Thus answer is option A, 25 centimeter. So depth on the beam comes out to be 25 centimeter. So this time I just use the trick for the rectangular section is tau max is equal to 3 by 2 times tau average, and tau average is what, force upon area, and force is 50 kilonewton and area would be width times depth, and that is BD. Moving on to the next question. Question number 16 for today's section is a horizontal beam with a square cross section is simply supported with sides of the square horizontal and vertical and carries a uniformly distributed loading that produces maximum bending stress sigma in the beam. When the beam is placed with one of the diagonals horizontal, the maximum bending stress will be. So this is quite a tricky question. I would left this question to you all. I'll help you in this regard. Is so so for this regard, I'll just let you know. You're given with a simply supported beam with a UDL W, length of the span rod stake is L. Our bending moment diagram would be parabolic with the WL square by 8. Thus maximum bending moment is WL square by 8. Now using the flexural formula, you need to calculate P by R. Using the first two relation, you just compute sigma for the cases. Now there are two cases. Case 1, when case 1 is when a section is simply supported with square, horizontal and vertical when the okay, so case 1 is when our cross section is this. So let's say this AA, right? So for this I would be what? A to the power of 12 and y would be a by 2. Thus sigma would come out to be m a4 by 12 times a by 2, and that would be uh, 6m by aq. Okay, now case 2 is this. When one of the diagonal is horizontal. So what will differ in this case is I and y, and you just compute the stress here and compare the relation with the above. Okay, I'll leave this part for you all to solve. Now moving on to the next question. Question number 17. A simply supported beam AB of span length 4 meters supports a uniformly distributed load of intensity 4 kN per meter spread over the entire span, and a concentrated load 2 kN placed at a distance of 1.5 meter from left end A. The beam is constructed of a rectangular cross section with width 10 cm and depth 20 cm. The maximum compressive stress developed in the beam due to bending is so seems like a very big question, but it is easy. Just we need to take it step by step. So this is a simply supported case, right? Simply supported case. Uh, uh, with a span length of 4 meter, right? And let's say if I write it as L. So now we are given with there's a UDL acting, right? Uniformly distributed load of intensity 4 kN per meter, and there is a concentrated load 1. Concentrated load 2 kN that acts 1.5 meter from left hand. This is A, this is B, and we're given with the cross section B is 10 centimeter, or I'll write 100 mm, and depth is 20 centimeter or 200 mm. Okay, most things have been written down. Yeah, so for this we just need to compute the bending moment diagram, okay, so that we can find what would be the maximum bending stress. Okay, yeah, so let's do this. So we need to calculate the bending moment diagram first. Okay, so let's do that first. Calculate bending moment diagram. I'll just take this as C and at the center as D. Okay, yeah, this would be 2 meters. Now uh, mm, uh, okay. So first we need to calculate the reactions at endpoints Ra and Rb. Take moment about b equal to 0. This would imply that Ra times 4 minus 2 into 2.5 minus 4 into 4 total length into 2 equal to 0. This would give me Ra times 4 is equal to 2.5 into 2 5 and for 16 to 32 32 37 Ra is equal to 37 by 4 this is equal to 9.25 kilonewton. Now to compute Rb, Ra plus Rb would be equal to 2 plus 4 into 4 implies Rb equal to 16 to 18 minus 9.25 and that would be 8.75 kilonewton. Now let us compute bending moment diagram. So for section AC, bending moment diagram is mx is Ra times, that is 9.25 times x minus 4x square by 2. So this is 9.25 x minus 2x square. For section CD, mx is 9.25 x minus 9.25 x minus this is the same 2x square minus this time this additional 2 comes in with x minus 1.5. Similarly for section DB, mx is equal to 9.25 x minus 2x square minus 2x minus 1.5. Or we can write this also minus 8.7. Okay, 8.75x. If I am coming from right hand side, uh, minus 2x square. So this is kind of 7. So let's draw the bending moment diagram. So everything is quadratic, we can see that. Okay, so at x equal to 0 it would be 0. Bending moment diagram. At x equal to 0 it would be 0. At x equal to 1.5, this would be equal to 9.25 into 1.5 minus 2 into this would be value comes out to be 9.375. Now let's see it in the center, that is like 2, right? So 7.25 into 2 minus 2 into 4 plus 3, that is kind of 9.5. At the end it will be 0. So since it's a quadratic, we'll just this as well as this as well as this. It won't be a smooth here, but let it be. So we can see design maximum bending moment. Okay, so this is A, B, C, D. Maximum bending moment comes out to be 9.5 kilonewton meter. Now coming into the to compute maximum compressive stress, we use the flexural formula M by I by sigma by Y. So sigma would be equal to M by I times Y. M is 9.5 kilonewton meter, that would be 9.5 into 10 power 6. I is BD cube by 12. B is 10 centimeter, 100 into 200 cube by 12. T by 2, that is 200 by 2. This would give me 9.5 into 10 power 6. 100 into 200 to the power 2 by 6. Now let's calculate this. 6 centimeters. This comes out to be 14.25 megapascal. The answer is 14.25. Okay, so answer is 14.25 megapascal. And let me see, 14.25. Out of all the 4 options, 14.35 is the closest one. So we can choose this 14.35, or else the correct answer would be none of the above. Okay, moving on to the next question, and Probably the last question of today's session. Question is: a structural beam is subjected to sagging bending moment, not bending moment, it's a bending moment. Has a cross section which is an unsymmetrical I section having overall depth of 300 mm. The bending stress in the beam at the top and bottom are 200 megapascal and 50 megapascal respectively. The position of neutral axis in mm from the bottom flange is, and options are 60 mm, 120 mm, 240 mm, and last option is data is insufficient for the determination of neutral axis. So, so this is a simple question but a tricky one. So we need to compute the neutral axis, and okay, so let me draw something. Not sure what was the case. Kind of there is an unsymmetrical I section. Okay. And there is say neutral axis is somewhere here. I don't know. If I write this is say yt and yb. So okay, let me draw till here. Yb. Okay, this is the bottom flange. So and total depth is provided, right? Yeah. So depth, this is equal to 300 mm. We need to calculate this yb, neutral axis, distance of the neutral axis from the bottom flange. We need to calculate this yb. So we are given with is that the bending stresses in the beam at this top and bottom are equal to 200 megapascal, and I will just write sigma t is equal to 200 megapascal and sigma b is equal to 50 megapascal. Our top, bottom. Okay. So if you remember the flexural formula, it's m by I sigma by y E by R. Using the first two relation, we can write m by I is equal to sigma by y. Okay, now for the top part, since moment would be the same, so m I would also be the same, sigma top by y top. This would be equal to sigma top is 200 and y top can be written as d minus yb. Okay, now similarly we can write for the case of bottom one, sigma bottom by y bottom, and this is equal to 50 by yb. 1 2 from 1 and 2 we get 200 by d minus yb is equal to 50 by yb, that is 200 is equal to 50 d minus yb, and 200 yb is 50d minus 50 yb. It is yb is equal to 50d by 250. Okay, we are given with the value of depth. D is 300 mm. So first thing, this would be equal to d by 5. So yb is d by 5, d by 5, and this is given as 300 by 5. Yb comes out to be 60. Correct answer is option A, 60. And if the question would have been the position of neutral axis from the top flange, then the correct answer would have been 250 mm. Okay. Yeah, so this is it. There's question number 19 also, but we have discussed a similar question earlier, so I hope that you guys can work around this question. This is for your exercise. In this, only certain data has been changed, while the pattern of the question is similar. You just need to find the maximum load carried by the timber when the maximum permissible stresses in bending and shear has been provided. Okay, so this is it for today's session. This concludes the 8th discussion session. The next discussion session would happen in the normal timing, that is on Saturday 4 p.m. to 6 p.m. So see you for the 9th discussion session on this coming Saturday. Have a nice day all. Take care.